The construction of a footbridge over the Słupia River is a key element of the Pomeranian International Bicycle Routes R10 and Vistula Bicycle Route R9 project, specifically covering section R10 within the cities of Ustka and Słupsk. This modern infrastructure aims to enhance cycling connectivity and promote sustainable transport along internationally significant bike routes. The footbridge will span 58.5 meters, offering both cyclists and pedestrians a safe and scenic crossing over the river. Designed with durability and aesthetics in mind, the structure integrates seamlessly with the surrounding landscape. The total cost of construction is estimated at 39 million Polish zlotys, reflecting the project's ambition to create high-quality, long-lasting infrastructure supporting regional mobility and tourism. Destiny Bridge is the signature structure of the Cross-Tay Link Road project, designed as a balanced cantilever bridge featuring 56 cast-in situ deck segments. A notable innovation in this project is the use of non-symmetrical casting. Initially, only one Form Traveler FT is used to cast a single segment. Afterward, this FT is relocated to the segment's end, where a second FT is assembled for casting the pair's matching segment. Following this setup, segments are cast symmetrically. The bridge includes segments up to 5.6 meters in length, 15.44 meters wide, and weighing as much as 261 tons at 4.6 meters. Significant progress has been made, with 12 of 14 segments completed on the east span and 10 of 15 on the west. Backspan preparations are advancing, and the east stitch pour is imminent. Additionally, a 324-ton precast portal structure with 27-ton roof units has been installed to provide local access. The Raunheim Viaduct, located at the complex Mönchhof Interchange near Frankfurt, Germany, was a key element of the region's transportation infrastructure. As a three-level crossing, it facilitated the movement of thousands of vehicles daily, connecting critical motorways such as the A3 and A67. However, due to structural aging and the need for modernization in line with current safety and traffic flow standards, the viaduct was recently decommissioned and successfully demolished by Maxwell GmbH, a company renowned for its expertise in demolition and civil engineering. The Mönchhof Interchange is one of the largest and most heavily trafficked highway junctions in Germany. The Raunheim Viaduct had served as a critical overpass within this network, but over time, its design no longer met the demands of modern logistics and vehicle volumes. After a thorough evaluation by infrastructure and transportation authorities, the decision was made to dismantle the structure and replace it with a more efficient and safer alternative. Maxwell GmbH, known for its precision engineering and environmental responsibility, was awarded the contract for the demolition. The company implemented a carefully planned and technically sophisticated process to bring down the viaduct, ensuring minimal disruption to the surrounding road network and local communities. Given the scale and complexity of the three-level crossing, the demolition was carried out in multiple stages. Special attention was paid to traffic safety, noise reduction, and the recycling of construction materials. In addition to the physical challenge, the demolition required close coordination with various stakeholders, including traffic management authorities, environmental agencies, and local municipalities. Maxwell GmbH employed advanced demolition equipment and techniques, such as high-reach excavators and controlled dismantling, to complete the project efficiently and safely. The removal of the Raunheim Viaduct marks a significant step toward modernizing Germany's highway infrastructure. In its place, a more contemporary and resilient design is expected to rise, improving traffic flow, reducing congestion, and enhancing road safety. The Charles J. Miller Road Bridge, located in McHenry County, Illinois, has played an important role in the region's transportation infrastructure. Originally constructed in 1988 by the McHenry County Division of Transportation, the bridge was built to serve the growing traffic demands of the area. As time passed, increased development and population growth led to heavier usage of the road, highlighting the need for expanded capacity. To accommodate this growth and ensure safe, efficient travel along Miller Road, county officials proposed the construction of a second bridge. Positioned just north of the original structure, the new bridge was part of a broader initiative to improve traffic flow and reduce congestion, especially during peak travel times. Construction of the second Charles J. Miller Road Bridge began in 2012 and was completed in 2013, taking approximately 1 year. The project not only provided a modern and structurally sound crossing, but also enhanced transportation efficiency by allowing for additional lanes and better traffic management. This second bridge helped meet both current demands and anticipated future needs, supporting the long-term infrastructure goals of McHenry County. The bridge replacement project on County Road 104 at Mankins Branch in East Georgetown, Williamson County, Texas, was a significant infrastructure initiative aimed at enhancing safety and transportation efficiency in the area. The original bridge, which had become functionally obsolete, was replaced to meet modern standards and accommodate increasing traffic demands. The project was a collaborative effort between Williamson County and the Texas Department of Transportation, TXDOT, with funding provided by both entities. The engineering design was undertaken by Steger Bizel, a reputable firm known for its expertise in civil engineering projects. The construction contract was awarded to Chasco Constructors, a company with a strong track record in executing public infrastructure projects. Construction commenced in September 2010 and was completed in May 2011, adhering to the planned timeline. The project scope included the complete replacement of the existing bridge structure and the improvement of the approaching roadways to ensure seamless integration with the new bridge. Financially, the project was initially estimated at $775,000. However, the final cost amounted to $2,247,003, reflecting the complexities and unforeseen challenges encountered during construction. Despite the budget increase, the project successfully delivered a modern bridge that significantly improved the safety and reliability of the transportation network in the region. Reconstruction of the Opdyke Road Bridge just north of Auburn Road marked a significant infrastructure improvement project in the area. Work commenced on June 18, 2018 and was successfully completed on December 14, 2018. The project was undertaken to replace the aging structure, enhance safety, and support growing traffic demands in the Auburn Hills region. During the 6-month construction period, the existing bridge was fully removed and replaced with a modern structure designed to improve durability and traffic flow. The new bridge features upgraded guardrails, improved drainage, and wider lanes to better accommodate vehicles and improve overall driving conditions. The project also included enhancements to pedestrian walkways, providing safer access for non-motorized traffic. Construction was managed in phases to minimize disruption, though temporary closures and detours were necessary. Local authorities and contractors worked to keep residents and commuters informed throughout the process, helping to reduce inconvenience and maintain traffic flow. The completion of the bridge reconstruction is a critical step in the broader improvement of the Opdyke Road corridor. Further resurfacing work is scheduled to take place in 2019, extending north of the new bridge to improve roadway conditions and ensure consistency in infrastructure quality along the route. The successful conclusion of the bridge project not only restores vital connectivity, but also lays the groundwork for continued improvements that will benefit motorists, pedestrians, and the surrounding community for years to come. The Hartford I-91 Bridge Replacement Project, formerly known as the Dutch Point Viaduct Rehabilitation, is a significant infrastructure initiative aimed at modernizing a critical segment of Interstate 91 in Hartford, Connecticut. Commencing in March 2025, this extensive project focuses on the 1,800-foot elevated structure that carries I-91 southbound between the Connecticut Convention Center and the historic Colt Armory. Constructed in 1964, the viaduct has been identified as requiring substantial upgrades to meet contemporary safety and structural standards. The primary goal of the rehabilitation is to enhance the structural integrity and safety of the Dutch Point Viaduct. Key components of the project include replacing the bridge deck to improve durability and load-bearing capacity, upgrading the drainage system to prevent water accumulation and related damage, installing new barrier walls and highway lighting to meet current safety standards, strengthening steel girders and replacing or repairing bridge bearings to extend the bridge's service life, implementing new micropiles and concrete encasement of steel pier bents to reinforce the substructure. These enhancements aim to extend the viaduct's service life by approximately 25 years, ensuring it remains safe and functional until a more comprehensive replacement is undertaken as part of the greater Hartford Mobility Program. The project is estimated to cost $91.85 million, with funding sourced from a combination of federal and state contributions. Specifically, 90% of the funding is provided by federal programs dedicated to highway and bridge maintenance, while the remaining 10% is covered by the state. Construction is scheduled to be completed by September 2026. Given the viaduct's central role in Hartford's transportation network, the rehabilitation project necessitates several traffic adjustments. One of the 3 southbound lanes on I-91 will be closed for approximately 18 months. The State Street on-ramp to I-91 southbound will be closed throughout the project's duration. Temporary nighttime lane closures are expected between 7 p.m. and 6 a.m., along with daytime shoulder closures from 9 a.m. to 3 p.m. Detour routes have been established to guide motorists during these closures. For instance, drivers can use the South Morgan Street on-ramp or the Sheldon Street on-ramp via Columbus Boulevard to access I-91 southbound. Additionally, I-84 eastbound motorists seeking to merge onto I-91 southbound will need to adjust to temporary traffic patterns due to the construction. The rehabilitation of the Dutch Point Viaduct is not only a structural necessity, but also a strategic investment in Hartford's future. By modernizing this vital corridor, the project aims to enhance safety for thousands of daily commuters and support the region's economic vitality. Local officials, including Hartford Mayor Arunan Arulampalam, have acknowledged the short-term inconveniences but emphasized the long-term benefits of improved infrastructure. A proven and cost-effective alternative to traditional asphalt paving is chip seal, a surface treatment used widely in places like Fleming County, Kentucky. This method has been gaining traction for its affordability, durability, and ease of application, especially on rural or low-traffic roads. The chip seal process involves several coordinated steps. First, a liquid asphalt emulsion, such as -2 rupees, is evenly sprayed over the existing road surface. This provides a sticky base for the next layer. Then, a spreader truck follows closely behind, applying a layer of aggregate, often referred to as eights, which is typically small, crushed stone. These stones are then pressed into the emulsion using heavy rollers, ensuring a tight bond with the surface. What makes chip seal appealing is its significantly lower cost compared to asphalt paving, making it ideal for municipalities with limited budgets. In the example from Fleming County, crews have covered 16 to 18 miles in a single season, demonstrating how efficient and scalable the method can be. To enhance durability, road crews often apply 2 to 3 coats of chip seal. Each additional layer increases the road's resistance to wear and extends its lifespan, making it more robust against weather and traffic over time. While it may not offer the ultra-smooth finish of traditional asphalt, chip seal creates a reliable road surface that performs well under most conditions. It's particularly suited for rural areas, where traffic volume doesn't justify the expense of asphalt, but road quality still matters. The Johnsburg Road Roundabout, completed in 2014, marked a significant milestone in McHenry County's transportation infrastructure as its first modern roundabout. Situated at the intersection of Johnsburg Road, Chapel Hill Road, and St. John's Avenue in Johnsburg, Illinois, this project aimed to alleviate long-standing traffic congestion and enhance safety at a complex, skewed intersection. The roundabout was a component of a broader $2.7 million initiative to widen and reconstruct Johnsburg Road from IL-31 to Chapel Hill Road. This comprehensive project included the addition of a continuous center turn lane, upgraded sidewalks with decorative brick pavers, enhanced lighting and landscaping to improve both traffic flow and the aesthetic appeal of downtown Johnsburg. Initially met with public skepticism, the roundabout has since been embraced by the community. Village President Ed Hederman noted that residents who were once concerned have become satisfied with the outcome. The Chenab Bridge, currently under construction in the Riasi district of Jammu and Kashmir, stands as a remarkable feat of modern engineering and a symbol of India's infrastructural prowess. Spanning the mighty Chenab River between the villages of Buckle and Kauri, The bridge is part of the ambitious Udhampur-Srinagar-Baramulla Rail Link (USBRL) project, a landmark effort to connect the Kashmir Valley to the rest of India through a reliable and all-weather railway network. The Chenab Bridge will rise 359 meters above the riverbed, making it the highest railway bridge in the world, 35 meters taller than the Eiffel Tower. The riverbed lies at approximately 324 meters below the bridge's arch span, highlighting the immense vertical drop across the deep and rugged Chenab Gorge. The tallest pier of the Chenab Bridge stands at 137 meters. To support it, massive foundations measuring 36.5 meters by 50 meters were constructed, ensuring stability on the steep Himalayan terrain. The slopes on either side of the Chenab Bridge site are extremely steep, with inclinations ranging from 43 degrees to a near vertical 77 degrees. This severe gradient posed major engineering challenges, requiring advanced slope stabilization techniques, including controlled blasting, rock bolting, and reinforced shotcrete, to ensure safety and structural integrity during and after construction. When completed, the Chenab Bridge will stretch 1,315 meters, 4,314 feet, in length, and include a viaduct of 650 meters, 2,130 feet, on the carry side. Its defining feature is a 480-meter, 1,570-foot, steel arch span, which will be the longest for a broad-gauge BG rail line in the world. What truly sets this bridge apart, however, is its height. It will rise 359 meters, 1,178 feet, above the riverbed, making it the highest railway bridge in the world, surpassing even the height of the Eiffel Tower by 35 meters. The Chenab Bridge is not just an architectural and engineering marvel because of its scale, but also due to the highly challenging environment in which it is being constructed. Situated in the young and geologically unstable Himalayan mountain range, the bridge's foundations had to be designed with exceptional care. The terrain on either side of the Chenab River features steep slopes ranging from 43 degrees to a near vertical 77 degrees, and the gorge itself is deep and narrow, making access and construction extremely complex. One of the most critical design considerations for the bridge was its ability to withstand natural and man-made forces. The bridge is the first in India designed to resist contact blast loads, which means it can endure potential acts of sabotage or explosive impacts. Moreover, it has been engineered to survive earthquakes of magnitude 8 on the Richter scale. Given the location's exposure to high-velocity winds, the bridge is equipped with sensors that monitor wind speeds. If winds exceed 90 kilometers per hour, deemed unsafe for train movement, the system will automatically stop train operations to prevent accidents. Given the precarious geological conditions, much of the work has involved extensive slope stabilization before the actual construction of the bridge piers. The tallest pier of the Chenab Bridge reaches a staggering height of 137 meters. To support such monumental structures, massive foundations measuring 36.5 meters by 50 meters were constructed. The stabilization process has been meticulous. It began with cutting and leveling of the mountain slopes using a top-down approach, followed by controlled excavation in 3 to 5 meter steps. The steep gradient necessitated a method called pre-splitting, which uses small, precisely placed explosives to separate rock layers, while minimizing damage to the surrounding rock mass. This careful excavation method was designed by the Indian Institute of Science, IISc, Bangalore, and proof-checked by the internationally renowned firm URS. Once the excavation was complete, rock bolts of varying lengths, 4 meters, 8.5 meters, and 11.5 meters, were installed to further stabilize the slopes. Shotcrete, a layer of concrete sprayed onto surfaces, reinforced with steel fibers, was then applied, along with weep holes to relieve hydrostatic pressure that might build up in the future. As of now, over 40% of slope stabilization work on the Bakal side has been completed. Executing such a complex project in a remote and rugged area comes with its own set of logistical challenges. Diesel consumption for heavy machinery is massive, between 15,000 and 18,000 liters per week on the Bakal side alone. Diesel has to be transported from Riasi, located 26 kilometers away, and similar logistical efforts are required on the Cowrie side, 40 kilometers from Riasi. Explosives needed for blasting operations also require secure storage and transportation, adding another layer of complexity.